So this is going to be a little bit more dry by comparison of some software minutia of this process than the fantastic results presented before. But we're going to talk about. It's still interesting. So just to introduce myself quickly, like I said, my name's Kiran. I'm a PhD student at Caltech working on two projects, the DSA 2000 telescope and this smaller project called the Global Radio Explorer, GREX. So I'm relatively new to radio astronomy, but I'm getting my hands dirty in the software a little bit, and I've found out some interesting things, and a big Julia user, so I'm trying to see how we're going to incorporate Julia in the process of specifically real-time imaging for upcoming radio telescopes. So if we look quickly at the architecture of specifically an FX architecture radio telescope, we'll have all these antennas, say N antennas, spread around a large area, not quite as big as the EHT, but say with the DSA 2000, a couple square kilometers. And then you have this analog signal path. All the information is digitized. Then that is channelized with a Fourier transform. Big transpose operation, where then you want to have correlations of every frequency channel, and those correlation steps need to receive every antenna. And then you have some science pipeline. So there's a lot of data crunching through this whole thing, and we're going to talk about specifically the last step of this process, which maybe the last two if you include some kind of software correlation, that is, if it were incorporated in the software and not some like ASIC or something specific. So if we try to look at how much data that is, we're thinking on order of hundreds of terabits per second at kind of the high end, which is insane when you think about it. We're talking about years worth of internet traffic in a month or so. And so how we actually write software that can do this is exceptionally non-trivial. And the way you parallelize it, like the specifics of how you parallelize it, become really, really important. And you can think that this data comes in chunks of which antenna it is, how many, if you're doing beamforming beams, polarizations, the channel itself. So it's quite complicated. So normally the way we tackle this is some kind of stream processing framework, because after you've digitized it, you want to do something. If it's making an image, there's quite a few steps before you actually make the image, such as removing radio frequency interference. You might want to do some requantization to a different bit depth. If you're doing transient pipelines, such as looking for fast radio bursts or pulsars, you want to do some dedispersion steps. Or if you're doing some time domain stuff like working on cosmic ray science, you'll want to do maybe FFTs or FIR filters, things like that. So how you do the stream processing, normally you want to parallelize these different operations. So while you're working on, say, if it's an FRB pipeline, you're working on the dedispersion step, you want to be capturing packets on another thread, right? You don't want to do all this at one time because that wouldn't make any sense. But again, like as with anything, there's pesky details for how you actually implement this. And an interesting question, the first interesting question is, how do you deal with back pressure? So you have this, a bunch of operations that are strung together in a pipeline. If one is occasionally slower than the cadence in which you're trying to process information, then it's going to have to pause upstream execution because that's the only thing you can do. So in some circumstances, that's okay, in some it's not. So how do you actually accomplish that? And of course, having some way to observe how what processes are being slow, etc., it really, really helps this. And if you're doing, most radio telescopes have some kind of heterogeneous compute where you're doing some processes on the GPU, some on the CPU, how you move the data, how that moving of data is incorporated into the entire stream processing framework. These are all kind of hard details to solve. So in looking at how to do this with my own telescope, GREX, the one I was told, the software package I was told to look at was this thing called PSR data, which has been around for a while. And the way it works is it's a C library that effectively just gives you an API for these ring buffers in shared memory. So you write programs that do a thing, and on the input and the output, you attach to these PSR data buffers, which shuffle data in, shuffle data out. It's operating on bytes. There's nothing really super special or magical about it. How you deal with metadata is a little bit tricky. It's usually just another set of ring buffers that you have to attach to. I have found this software to be rather buggy. And if anyone uses PSR data and wants a little bit less painful experience, I have a REST wrapper called PSR Data RS, which is, in my opinion, quite good. There's another library that Dave McMahon wrote, who's here and going to talk after me, called HashPipe, which certainly looks a lot better. And it, at the surface level, it seems it's a bit more homogeneous than PSR data. You have, instead of having these disparate programs, which then just have to trust that there exists these buffers somewhere in shared memory, it's Dave can correct me if I get this completely wrong, but as far from my understanding of it, you have this one program that kind of manages the whole thing, and you have these shared objects that are your tasks, and that's is a bit more higher level in how it's orchestrated, which seems nice. And then lastly, the one I've seen that some people use is Bifrost, which might be the closest to what if we were to start thinking about what this would look like in Julia, in that it has a Python kind of top to it and a C++ backend, where they have these library of blocks of operations that the user can use. And I think they're not expecting the astronomers to write their own blocks because it's in C++, just kind of put them together. But the people have been successful with this model, and it comes with a lot of nice tools. Like there's something which looks like top in how you can in the utilization of each tasks, things like that. But it's relatively complex in how it has been implemented. They have their own ND array abstraction, and if you want to add your own functionality, like one might want to do, you have to write external code to escape the interpreter lock in Python. To give you a look at what Bifrost looks like, this is pretty much an entire pipeline definition. In Bifrost, an FRB pipeline where you read from these SIGPROC filter bank files, copy it to GPU memory, do the transpose, do the an FDMT, which is a dedispersion step, copy it back to the host, and write back to a file. Pretty simple. And this will run with ring buffers in shared memory, just like PSR data does, so you can kind of smooth out the timing for moving data around and things like that. So if we were to think about doing something like this in Julia, the first, and I'm not even trying to argue that we should, but if we wanted to, because Bifrost is quite nice and people do use it, and we could do something similar, it kind of would make sense to use channels to move data between the tasks, because that's kind of the modern approach to how we share data between threads. And we can show that it can be just as fast as shared memory when used properly. And it's nice for the actual user, especially if they're used to working in C, they wouldn't have to do any explicit synchronization or mutex locks or unlocks, things like that. And something that I think is pretty important is, if you're using channels, you're getting this safe by construction setup, so you don't have to think about race conditions and things like this. And what I propose is that we could use Julia's metaprogramming facilities to come up with a domain-specific language for pipeline construction. So something like this. This doesn't exist. This is kind of what it may look like if one were to write that code, where the same as the Bifrost example, where you're reading from a filter bank file, moving it to GPU memory, doing a dedispersion step, and then coming back to writing a SIGPROC file. And I'm kind of modeling this off of the chain.jl syntax, where you're listing these chunks of operation, but instead of function composition between them, you have the same kind of ring buffer-like thing to connect the data together. And you could even, because you obviously want some parts of it that don't have ring buffers so you can save on memory. You could have a block like I have with the named block GPU here, that you only have these two channels going into this GPU block and out of it. So I think that's kind of a nice little approach. And the questions later I want to hear your feedback on this. But what does that block do? Like I said, it's going to create some kind of meta pipeline object that manages the lifetime of all of these things, creates the channels that connect them, and creates the tasks, can spawn the task based on the life cycle of the pipeline object, and will, of course, decorate some syntax for how big those channels are, things like that, whether or not you want it to be blocking or non-blocking, these kinds of details. So why would we do this? Well, compared to Bifrost, at least, it's a single language solution, which is nice because that means that if you are an astronomer and you don't know how to write or don't want to write C++, which is a very reasonable thing to do, you could write your own little custom processing thing and have it be just as fast, as the C++ block. The other thing is you get this pretty seamless GPU support with Julia. If you've used CUDA.jl before, I gave a talk last year at JuliaCon where I wrote a dedispersion kernel for fast radio bursts, and in my 20-line Julia solution, I'm just as performant as the quite large CUDA implementation that's used in a popular FRB pipeline. And I'm not particularly good at GPU programming, and if I can do that, then I'm sure the rest of the astronomers could write some absolutely incredible code. And kind of the last important bit is this could be accomplished pretty simply, I think. Bifrost leverages a lot of custom C++ in the background. Like I said, their own bespoke ND array implementation. They implemented their own JIT for some reason. And they have to maintain this library of custom blocks that they're expecting astronomers to use. So it's good for its purpose, but Julia would probably be much more flexible if this existed. And the ecosystem itself would be very, very helpful. We had this talk earlier today about thread pinning, and it looks so. One of the details in this, if you're working on like capturing data from 100 gigabit network card, the task that does that needs to be pinned to the same NUMA node as the network card, and we have this wonderful library in Julia now, thread pinning, which would make that very, very simple. And if we're operating on a big cluster, we have distributed.jl and Dagger, which there were also talks at the previous minisymposium. If we want to be really careful with reusing memory and not hitting the garbage collector as often as we could, Dave wrote a wonderful library called pool queues that we could kind of move stuff between the tasks with this queue abstraction, which is really quite nice. And of course, all of the GPU stuff as well. Why wouldn't we want to do this in Julia, though? Well, besides the fact that alternatives already exist, I'm a little worried about the timing kind of part of this and GC pauses. There was a talk from, I forgot which JuliaCon it was at, where they were doing real-time adaptive optics controls for an optical telescope, and had to mess a lot with the garbage collector to get it to really work in real time. I'm not sure how difficult that would be in a system like this. And related to that is the whole concept of packet capture. Both Dave's HashPipe library and Bifrost and PSR data provide some packet capture, because most radio telescopes, you're ingesting data as UDP packets at the very, very input if you're not reading from like a file. How do we implement high-speed packet capture in Julia? Would you even want to? We're talking about like using DPDK or some InfiniBand, something like that, which you might want to write that in C. Not sure, but who wants to write C? And kind of the last big thing from my list here is I'm not sure if Julia's channels are fast enough. I've written a similar pipeline kind of thing using channels in Rust for GREX, and it took the people who wrote Crossbeam, which is a channels crate in Rust, quite a long time to get it to be performant. And I haven't seen that kind of level of optimization done on Julia's channels. So that would probably need some investigation. But when they do optimize it, I easily got like 60 gigabits through channels on relatively simple hardware. And last little details, if you're building like a large scale radio telescope that's running on a cluster, I'd be a bit worried about how you would deploy it. Would you build would you use package compiler to like make the artifact that you actually deploy? Is that the right way to do it? How do you check for correctness in that thing that you deploy? Because we're kind of limited in static analysis tools a little bit. Although I saw some talks about JET, and I'll probably look more into that in the future. But yeah, that's my ideas. And I'm looking forward to your feedback on this before I spend any time actually trying to develop this into something real. Thank you.
All right. Thanks, Kiran, for that great talk. Do we have any quick questions before the next speaker? Okay. So do you think that Julia is the right thing for this, or do you think we should be looking at something like Rust?
I think for simple things, it probably would be, because I see people write simple pipelines in Bifrost, for example, for like FRB stuff, and it would be nice to have that in Julia, especially because if you're working on some, say, novel dedispersion algorithm, I'm gonna write that in Julia, like of course I am, and then having to try to shoehorn that into some pre-existing framework would be not so nice compared to having it all be in Julia. But is it right for like, say, the DSA 2000? Maybe, and we could talk offline if anyone has more thoughts on that kind of thing.
And
that's true.
And there's also a discussion that we'll be having from 6:10 to 7 tonight, or an open discussion where we can discuss these things as well.
For sure.
All right, let's thank Kiran again.